All right. So today we're finally talking diffraction and the electromagnetic spectrum. So you might have seen diffraction covered in like maybe high school physics or something. And if you think about it, what comes to mind? I'm guessing like interference maybe, or like shadows maybe. These are some things that might look familiar to you or similar images. So this one is a plane wave passing through a slit. And then you can see sort of these like circular things going outwards from the edges. This is a shadow of a pencil that is sort of just goes to infinity there. And this is matter wave diffraction, so on a tiny scale. These are from Hecht. And has anyone heard of the single slit experiment? Or so this was done historically by I forget. Whoops. Anyway, so a physicist shone a light through a very small slit, right? And essentially what we see here are wave fronts. So what is a wave front? So each of these lines, let me annotate. So it's essentially like, and I can't find oh, there we go. So essentially when we think of waves normally, we have this is like the usual depiction of waves, right? So the wave front is like if you're looking down on it, kind of like this with your eye here, what are you going to see? In these diagrams, what is labeled is essentially the peak here and the peak here. So if you can picture, so like a plane wave is usually drawn like this. And essentially what's happening is you're going from a peak to a trough, and then from a peak to a trough to a peak, and then a peak to a trough. Does that make sense? If people can picture that. So you're looking at the wave from the top, and then if you have a spherical wave like this, yes, very spherical. You're going once again from a peak to a trough here, trough to a peak here, and then peak to a trough here, and trough to a peak here, like same idea. So get rid of these. And oh, that worked. Okay, and then so here what we have is each of the wave fronts coming from a different place here is a spherical wave, right? So we have spherical waves going through like every part of this aperture. And so what happens is that, well, they interfere. So interference, you might remember, is just when you have a wave. That's a terrible wave. When you have a wave, and then maybe you have another wave that's slightly displaced. Then they sum. Well, you're gonna get here, you're gonna get twice the amplitude, and somewhere like here, right, where you have positive and negative, you're gonna get a 0. So it'll end up like this, and then it'll cycle. Or you can also have interference of waves of different wavelengths, and essentially it just adds, right? So here what actually happens is you end up with something like this out here, because the center is the least obstructed, right? So you get the most constructive interference here. And then the further you go out, the more it sees the effect of the blockage, right? And because light spreads as a spherical wave, spreads, right? So this is what happens on a single slit experiment. And this actually is also true for, it's not just photons, but here we're talking photons. because we can get into like probability distributions and probability density and stuff. But essentially, like, do we want to talk this? We can come back to it actually. Okay. So there's also a double slit experiment. So instead of one, we just have two little slits. And here we have an incoming plane wave that I just talked about, right? And what happens is you get these spherical wavefronts diverging from each one. And the two, well, actually there's, yeah, you can think of it as two start interfering, and you can see wherever they overlap, that's actually constructive because it's the peaks of both, right? And then wherever like in the middle of these is they're like the troughs, and whenever like a middle of a peak of one collides with the trough of another, we get destructive interference. So this is kind of what we see instead. Yeah, this is called Young's double slit experiment. I can't remember if Young did the single slit as well, but we can double check that. Okay, the electromagnetic spectrum. You've all seen this. So we have the rainbow essentially in the visible range. So that's about like 400 to 700 nanometers ish. Then we're starting to edge into the infrared. Like a pretty common optical instrument, like a helium neon laser, is about here, and it's red, and you can see it. Some of the optics labs on campus have them, and it's used for like calibration, alignment, whatever. And as your wavelength decreases, right, it means your waves are getting shorter and shorter, and it also means that your waves oscillate more and more frequently, and the higher the frequency, the higher the energy, right? So we have ultraviolet, X-rays, gamma rays in like the super short wavelength range, and then the longer we get, we go into IR, and that's what we're working in. Like IR got neatly bundled up into one thing here, but in reality, like when we talk remote sensing, we actually care about like a much more detailed breakdown. Like, am I annotating? There we go. We have shortwave infrared, midwave infrared, and longwave infrared. So in shortwave infrared, this is about, so we said visible goes up to about here, right? Shortwave infrared goes from about 1,000-ish to like maybe like 2,500 nanometers, about that. And there's very certain detectors that work in this range, right? And we chose an InGaAs, an indium gallium arsenide detector, because they can actually see these wavelengths specifically for it. And then the further you get out into here, actually the same, spectroscopy techniques still work, but you just have to make sure your equipment and everything is adjusted to actually detect all of those and be able to, transmit when you want it to transmit and absorb when you want it to absorb, all of that. But when we get into longer wavelengths, we start working, yes, sure, like we can use meters and stuff. But typically for convention, what we actually do, I don't know why, is use wave number instead. So like, yeah, in these longer ones, especially in the infrared, you're always going to see stuff in wave numbers, and it's annoying, but wave number is just 1 over wavelength. So K is wave number is 1 over lambda, and for some reason it's in inverse centimeters. So you're gonna see like nanometers, which we're using, microns, which are also really common. It just 1000 nanometers is a micron, and then on the other hand, you have inverse centimeters. But yeah, like then you have, well, radar, radio, radio, radio. Yeah, that's kind of the spectrum. I guess different parts of the spectrum also encode different information. Here we didn't talk about, absorption lines and you can't see that, absorption lines and emission lines. So if you look at the sun spectrum, right, you see all these lines that are missing. And also when you look at, this, when you look at a, like, let's say a sodium lamp, which is just Na, you also see particular lines. So those are like the signatures of specific elements, right? And we have both emissions lines and absorption lines, but they are always in the same locations. So can anyone guess like an example of a case of emission and a case of like absorption? It really is like situation dependent, but you see the lines in the same places. Oh wait, I see a message. Fun fact: the color pink is a fraud. Why? I'm wearing pink right now. Am I a fraud?
Well, pink isn't in the rainbow. It's a fake color.
What if you took this and made it lighter?
Well, you get pink from purple and red, right? Like it's the missing color if you loop the rainbow around up on itself, and that's the bridge. Yeah.
True. Wait, true. Pink is a fraud. Okay, so what do you think about?
I was thinking like sunglasses. Yeah. Do you get
oh,
well, sunglasses, they're polarized, right? So you
that's a whole other topic.
Yeah, but do they also, I think they also, some filter out like UV, right? So that'd be like a missing band in the UV coming through the lenses, right?
Although that's a different phenomenon, I would say. What I'm thinking of is like in a specific line, like at a very particular wavelength that corresponds to an element. Like for example, well, okay, let's talk Finch eye, right? We are 1590 to 1690, and within this range, at about 1650 nanometers, we have a dip in the line. So you're gonna have like some background, whatever. The background is gonna look a certain way depending on how much radiation in that range that is present. And then let's say this is 1650. There's a dip. Pretend that's a nice dip. And this corresponds to methane. And this is because the air, this spectrum I'm talking about is coming from the air. The air contains methane molecules in it, and methane molecules are absorbing light of this frequency or this wavelength. Why? If we want to talk about that, it's because you're actually going down to the molecular structure of things. So and the symmetries of the molecules. So molecules and atoms go through like energy transitions that have to do with like electrons and their shells and stuff. So there are particular transitions in different molecules that correspond to very specific energy levels, right? And so this is why different elements, specific elements, like specific wavelengths, because as I kind of mentioned, each wavelength corresponds to an energy, right? And so when you have a particular energy transition, if you've seen this plot of like these transitions, maybe in physics, that's a very like of like the different shells with different energies corresponding to them. This is what we're talking, and each of these, maybe I should have pulled out OneNote today, but hopefully annotating is okay, corresponds to like a particular amount of energy, right? And then that energy corresponds to a particular wavelength, and that wavelength is where we're going to see if it's a gas we're looking at, a absorption, because light that is otherwise present is absorbed and it's gone. So that's an example of absorption of methane. Emission can happen because we excite something. So yeah, so okay, let's see. Okay, well, okay, let's talk x-rays. I've been doing this advanced lab experiment, driving me a little crazy, but so I'm essentially shining x-rays at all sorts of samples. Fun fact, I was shining some x-rays on some like 16th century Chinese coins that they just have in the lab for some reason, and it's really cool. And so what happens is that you have these like high energy particles hitting something, right? And what happens is when you gain energy, nope, hold on, I'm getting things backwards. Hold on. Wait, no, actually, scratch that. I think there's actually like 7 different ways you can get a spectrum from x-rays, and I won't go into that, my bad. Okay, so let's say we're talking an atom and we have electrons like here, right? When an electron drops a shell, which is lower in energy, there's the excess energy has to go somewhere, right? So then it goes out as well, like it can emit a photon, and the energy of that photon is going to be, it gets a particular amount of energy that corresponds to the particular transition, and so you can map that on the spectrum. Yeah, you can do this in the lab as well, but yeah, so wait, there we go. Okay, so that is kind of emission absorption. Hope that made sense. Then we have the diffraction grating. So this combines sort of the interference, the double slit experiment thing that we talked about, right? So a grating can be made in different ways. Like modern gratings, there's so many different ones. Like, for example, we have the grism, which is really fancy, but one really simple way to make it is just put a lot of neighboring slits, and by varying them, you can get this, you can control the interference that you get out of them, right? Where the constructive interference happens is it's the most intense in the center, and as you go out, the adjacent peaks are called the different order diffraction peaks, right? So then yeah, we go 0, 1, 2, 3, 4, and usually we are after the first order, but so essentially what happens is you have a, like, let's say white light entering, and then what happens is that the different wavelengths are going to interfere differently because, well, let's see, can I draw this very well? Let's say red light looks like this, and green light looks like this, and then maybe my blue light looks like this. So you can see how the peaks and troughs, they're out of sync, so they are going to diffract differently, and And because we manufacture our grating to process a certain wavelength range and to like target a certain geometry, then we can like get a really nice rainbow out of it. And this is so yeah, this is a grating works through interference. You can also do this with a prism, right, which is a different it's a slightly different mechanism. But I think I'm at time, I guess. Do you have questions? Oh wait, I see the chat. Sodium D lines for emission. Yes. Okay. Thank you, Maggie. And Fizz Squad. Okay. My bad. I haven't been checking. Hopefully, has anyone tried to enter the call? Okay, good, because I think I'm the only host today for the Zoom. Okay. Any questions or anything? I'm gonna
What are the what's the purpose of the different orders? Like, why would we prefer to use order 1 as opposed to 0 or 2, 3, 4?
I think we can choose them. The first one is the clearest, right? With the problem with the 0th one is that I forget. I'm gonna look this up and actually get back to you. I remember reading about this. So the adjacent orders, the further you get, the less intensity you're going to have, right? Because in reality, your grading is finite. If you had an infinite plane of these slits, it would be a different story. But like, oh wait, no, hold on. No. Not because your grading is finite. It's because the further you go out, this as you sum up these interfering waves, right? Like the closer you are to the center, the more constructive interference you have, and then it dies outwards. So it's just not as useful, I guess, because we have less signal. Like going back to like, for example, like you can see kind of this kind of thing, right? Why can't the 0th order? Let me see if I can.
Well, the 0th is the one that doesn't exhibit diffraction, right? It's just straight through white light.
I think it's because if you have hold on. Okay, what I drew earlier, right, with the different wavelengths. Let's say that this is the 0, right? And that's one wavelength. And let's see if I can draw this. This is another wavelength. Right, and then like this is another wavelength. What happens is that like it just sums back up again, I think. Like when you get the interference at the screen. I think that's what happens at 0. I have to double check. So yeah. And yeah, because as you go out, the wavelengths shift and because they're different, they have different periods. But yeah. Okay. I guess I can stop it here and then hand it over. I think I went way over time, but it's a chill meeting today. So
yeah, I expect